All right, this is one of my favorite concepts in the geometry curriculum, so watch out. It's about compositions of transformations. Namely, what happens when we start doing multiple reflections. But there's a little bit before that. And also, you might be interested to know this is the one section that leads to some kind of theorems on the theorem sheet. We don't have much of that this unit. Okay, so this is about basically taking one transformation after another. In the log unit, you might remember when we did stuff like f of g of x kind of stuff. We did f of g of x. This is going to be the same kind of thing, but now we're taking a transformation of the result of a transformation, and this is kind of showing how it's related to algebra. Okay, when a transformation is applied to a figure, and then, yeah, we already talked about that. That is called composition. It's called composition in, I'm just looking at this. It's also called composition in algebra, so that should make some sense. Okay. The kind of the big news here that, I don't know, will be bigger news if you go on to take the AT geometry class. The fact that if you compose two isometries, you're going to get an isometry. We said isometries are those kinds of transformations that preserve distance, or we say that they are congruence transformations. And I don't know if this feels like it's come up enough in all of the videos and all of the class time yet, but something that, if it's an isometry, like a reflection or rotation or translation, if there are 2 points that are a certain distance apart before they get transformed by one of those things, and then after they get transformed, there's another version of it. They would be, if they're congruent, that's considered an isometry. This theorem is just saying, and this theorem's on the sheet, but it's really not very important for this course, but it's kind of a big deal in the world of geometry and mathematics, that it's saying that if you have one isometry followed by another isometry, the resulting transformation is going to be an isometry. And I think that's pretty easy to figure out, because if you don't change the length of something in either transformation, then it's not going to change from beginning to end if you do two of them either. So that seems kind of silly for now, but it is a big deal in a broader context, which I'll go on and on about if you let me. So I'll stop talking now. Okay, here's the last one to complete our list of all possible isometries. Then there's this one called a glide reflection, and it really does feel like a two-step motion kind of thing, but they want to call it an isometry because then I'll cover all the isometries. Again, this is another thing I'd like to go on and on about, but I'll try to keep it brief here. Basically, this is the kind of reflection, or sorry, this is the type of transformation you get if you are walking. Okay, I'm going to try to draw this. It's going to be really bad. This is known as kind of like the footprint transformation. So if this is one of your feet and you're walking, and okay, that's really bad. I don't know who has feet like that. And you're walking, and this is kind of like the center line. If you're walking, you take your next step, and it kind of goes like this. I'm walking sideways. And then you have another step, and it kind of looks like this. And your feet are getting smaller. No, that's not supposed to be true. And you're walking that way. Your footprints, those look at all like footprints. Footprint. There's two things going on here. You're moving in this direction, and like a translation, but at the same time there's also a left and right foot kind of going on here, so there's a bit of backwardsness going on. Yeah, I'm going to erase this before anybody screenshots that. That's pretty bad. But yeah, the nickname for this one is a walk, because we are translating, but we're also using opposite feet. So there's like a reflection and a translation is what they're talking about here. So reflection is a composition of a translation followed by a reflection in a line parallel to the translation vector. So if you were actually doing footprints, I'm going to try this again. I want to make right triangle footprints. And you go from that one to this one. Oh gosh, you can't tell where my right angle is. The right angle would kind of be here. So there's a right angle and there's a right angle. There's a translation followed by a reflection. So the translation would be here and the reflection would be in this line. I hope you can kind of imagine how that would work. We will have more time to practice that if you don't right now, and that's okay. So there's the steps. You make the translation. You make the translation here in the first place, and then you reflect. As long as the translation vector is parallel, so it's supposed to be parallel, as long as this thing is parallel to this thing, then it actually doesn't matter if you do the reflection first and then translate, or you do the translation first and then reflect. You can pause that and watch that again if that didn't make sense. Okay, example 1. Find the image of point A after translation. t and a reflection over the y-axis. Okay, so right now these aren't parallel. This little vector here is not going to be parallel to the y-axis. So this is kind of a misspelled. I call that misspelled light reflection. So it's not a great first example, but it is going to show a composition of isometries. So kind of like to this first theorem 9.1. It's a composition of isometries. It's going to show that it's an isometry. All right, point A after translation, x minus 3 y. Sorry, everything just kind of went away. I think I hit the button with my hand or something. Hopefully this is still going to look good. This is like what we've been doing in the other lessons. We would say this is a translation in vector -3 +1, which is the vector that takes the 0, 0 point to -3 +1 over here. So this is the kind of trip that all these points are going to take. If I do that to point A, and we'll do the next one in class. If I do that to point A is going to go here in the first place, and then reflect over the y-axis. So I don't really need to talk about what. So when point A kind of goes there, it does the -3, 1 thing. It ends up at this point, and then I reflect it over the. Did it say y-axis? Yeah, y-axis reflection is going to take it here. So this is where I have to go. I don't really have to name that point or notate it or anything. I just kind of have a blob there. That blob turned out to be really big for some reason. It's fine just sitting there. But this is the result. This is the answer for part A, is that one right there. I'm kind of thinking then that means we should do this one in the practice at the beginning of the next class. It's a little bit harder, or a little bit more to do. Describe the transformations that takes the regular one to the double prime. Okay, so these composition ones are being a lot about that. It's going to be, let's take it 2 steps down the road. They show you the first transformation. They say like first this triangle kind of went here, and then it kind of went there. Describe them in order, and yeah, the order does make a huge difference in these things. Okay, so first it looks like we had some kind of translation. If you have a hard time realizing that's a translation, ask me in class, but that's a translation. It happened again. I hope I didn't lose you. First, we're going to say there's... I'm even going to say it this way. First... and it changes color every time I do that. I like red for answer key. Translate... And how's that translation go? It looks like it's going... how far is this? It looks like... Okay, happened again. I flipped my iPad over so that maybe I won't hit the dang button with my left hand. Okay. It went -6 that way, and it went down this way. From Q to Q prime, it went down 3 and 6 to the left. Then, we're saying, that was to go from the regulars to the single primes. Then, from here to here, it looks like this was a reflection. And again, we'll talk more in class about how you can identify quickly, oh, that's a translation, that's a reflection, that's a rotation. This is a reflection, and if it's a reflection, it's a reflection over this line right here. Again, hopefully that's pretty obvious to see. Reflect over the line y equals -1. Is that correct? Is that the line y equals -1? I think it is. So, how do we write this notation? Remember when we were talking about f of g of x thing, like which happens first in f of g of x? Well, g of x happens first. So, if we do the translation and then we do the rotation, we have to notate that this way. So I have triangle PQR. The first thing that happened to it was that it was reflected over y equals 1. No, I'm sorry. The first thing that happened to it, order makes a huge difference. The first thing that happened to it was that it was translated. What? What is going on with my... Oh, I keep hitting other things with my hand. I don't know if you just saw what happened there or not. Oh my gosh. There's the PQ. All right, we're going to try to get rid of this. Hopefully that doesn't take too much of your time. It was translated... Yeah, it was translated by a vector of -6, -3, and then that whole thing got reflected. So I write the reflection over here by y equals -1. So that's not a huge lot of room. I'm gonna give myself some room. Reflected over y equals -1. So from left to right, it kind of looks a little bit different. I have to write the reflection on the far left because it happens second. Okay, so here we are. Find this double transformation, A double prime, B double prime, C double prime, if I reflect over this and then this. Now, if it wrote this in notation, I'd have to write this as R x equals -1 followed by R x equals 6. But they kind of explained this in words, and I put whatever the target is here. I guess it was triangle whatever, right? This would just say triangle whatever the triangle is. But they actually tell you in words here is a little easier to follow. But if you want to see the notation, that would be how the notation works. Okay, so I'm supposed to reflect this over when they gave me the lines here, which is nice. All right, C is going to go right there. A is going to go 3 points farther. This is the single prime version. B is going to go 5, so it's right above A, so it's right there. And then I'm not even going to connect the dots here because I don't want to mess me up. This is B double prime. I don't want to take the time to do it. I don't really need that. I'm just going to do this. I'm just going to do this one at a time. So that's kind of what that looks like. Okay. All right. So the question here, and this leads right into the theorem, which I do want to do, is how else could we have gotten there in one step? Notice it flipped once and then it flipped again. But overall, how could we have just gone from this stage to this stage in one step? And it's in the next theorem. It's just like if you reflect, and if you can't see that right away, it kind of looks like what happened here is just the whole thing went like that. And that's exactly what happened. And that happened, part of the reason why that happened is because these lines are parallel. So let's talk about this theorem. When you compose reflections in any two parallel lines, if you reflect over this line and then this line, and those lines are parallel, guess what? In the end, you're going to get all together what could have been just done in one translation. And I will prove that in class. Let's talk about, in class we'll do the proof. Or we'll do some sort of like demonstration or discussion of why. So that's going to happen in the beginning part of class. Like why does that always work out to be a translation? Okay, it's more than that. It's not just that it makes a translation. There's something very predictable about that translation. Like maybe we should go back to this example and look at this. This translation, not only is it a translation, but it's in a translation that, if you look at it closely, is in a direction that's perpendicular to those lines of reflection. And if you think about the other thing so direction is one thing that's important about a vector. The other thing that's important about a vector is how far it is. And that translation vector that seemed to happen here seemed to have a length of, I'm going to guess 14 because I know the rule and I don't want to count really fast. That has a length of 14. What does that have to do with the distance between those two lines? Well, lo and behold, that happens because the distance between the two lines was 7. All right, now let's just take that and think about that as we look at this theorem. The composition of two reflections in parallel lines can be described by a translation vector that is perpendicular to the two lines and double the distance. And again, we'll add that to things we want to prove next class. So I like to just draw this. Whenever you have two reflection lines like this, what you end up getting is a vector that's exactly double the distance between the two lines. Something like that. Okay, and I have this D and 2D here. It's pretty nice. Okay, when we say distance between the two lines, we always mean the perpendicular distance between the two lines. That's how distance between two lines is defined. Okay, example, do I want to do this in class or should I do this now? Oh, no, I have to do this one because this is not two parallel lines. This is the other theorem that's important in this lesson. What if I reflect this over R over P and then R over Q? So these are not parallel. This is a different kind of situation we're coming up with, and it's going to lead to a different theorem when we get to it. All right, reflect this over P first and then Q second. So reflect this over P, I can just do this kind of by eyeball. This isn't going to take long. That's A prime, that's C prime, and B prime is right above A prime, right? So this is B prime. Then I reflect that over the other line, reflect that over Q. A prime stays in the same place. C prime is going to go here to C double prime, and oh my gosh, I don't have any room to write because I wrote all over that area. Let me fix this real quick. This is a little bit different than what I'm used to. This is A prime, and gosh, why is my pencil so thick? And A double prime. Oh, that makes it thinner. A double prime. B double prime is here. So the triangle is actually here. Okay. So looking from beginning to end, yeah, my thickness is changing all the time. It's kind of interesting. From beginning to end, this is not a translation. Like what's happening from beginning to end to here, you might guess, kind of looks like a rotation. All right, let's talk about this on the next page. If you reflect in two intersecting lines, the result is a rotation. And not only that, we can use and it's exactly almost the same kind of proof, and we'll do the proof and the discussion of this in class. But it's very similar in nature to the proof of the first one. If you've got two intersecting lines, you get a rotation, and not only you just get any rotation, you get a rotation. So think about what we need for rotations. For rotation, if you think about the notation for rotation, we need a center and we need a magnitude in degrees. The center, of course, is no surprise. It's going to be the place where those two lines intersect, right? Because remember, we're trying to figure out what is the relationship between the two generating kind of lines, the two reflection lines. How do we know from those two lines what the rotation is going to be? Well, no surprise, the center of rotation is where the two lines intersect, and then the degree of rotation is going to be twice the angle that the angles meet at. So they have that drawn here. If this is angle x, the rotation angle is actually going to be double x. And there's a little more to it because there's also the direction of the rotation. What the way I like to think about it is if this angle from the first line, because this was if you look at the way these are labeled, this was reflected over K first and then L. Reflected over K and then L, the direction of the lines from line 1 to line 2 was this way. So the rotation direction is also going to go that direction. It's going to go, in this case, counterclockwise. So sometimes they say twice the measure of the directed angle, twice the measure of the directed acute angle between the two lines. All right, this is the last example we're going to do, and we'll be done. Just do this once. Reflect this over line 1 and line 2, and then let's talk about this as a rotation. Line 1 rotation, and I'm just going to kind of do this by eyeball. That's going to be E prime, and then I'm going to take this over line 2. It's going to be about there. You would do this with a ruler, and you would look a little bit better doing it. So from line 1 to line 2, the direction from one line to the other is that. So this is 60 degrees. We call that negative, don't we? That's the angle of the lines. So the direction, this rotation is centered at point Q, of course. But the degree of the rotation is, guess what? Negative 120, because it's twice the measure. Can't really see that. It's twice the measure. Okay, that's done. I'll see you in class.